In section 8.6, we're going to conduct large sample tests of hypothesis for the population proportion. So far we've been testing means. We can also do tests for proportion. So the test requirements are that we need a random sample selected from a binomial population. And then we need n times p0 and n times 1 minus p0 to be greater than or equal 15. That ensures that our p-hat distribution is approximately normal. Our test statistic, we're going to use the z distribution because our p-hat distribution is approximately normal when n is big enough. So it'll be p-hat minus p0, the hypothesized population proportion, divided by sigma p-hat, the standard deviation here of the sampling distribution for p-hat. And then p0, again, our hypothesized population proportion. So let's look at an example here. Apple's designed an improved, more durable screen for their iPhone. The shatter rate in drop testing for the old screens was 5.6%. They test 500 randomly chosen new screens. So the old screen was 5.6%. That's going to be our p0. That's what we're going to test against here, 0.056. And then they test 500 randomly selected new screens. That's our sample size, n is 500. Under the same conditions, and 22 screens shatter. So for us, a success, quote unquote, is going to be a shatter, because that's what we're testing, is the shatter rate. Is there sufficient evidence to believe the new screen is better? So better should mean that there's a lower shatter rate, a lower proportion. Alpha is 0.05. So first we do our requirements for the test. Random sample, and this was randomly chosen, so that's all set. NP0, so our P0 0.056, so NP0 is going to be 500 times the 0.056, and if you compute that on the calculator, you will get 28, and that is greater than or equal 15, and then n times 1 minus P0, so 500 times 1 minus the 0.056 gives us 472, and that is greater than or equal 15. So this one also checks out. So now we're set for our null and alternative. So the alternative, what we're trying to show is the shatter rate is less. So we're trying to show that the new proportion p is less than 0.056. If that's not the case, we'll assume that p is still equal to 0.056. We'll assume the new screen's at least as good as the old screen. Well, it might be worse because sometimes they do greater than or equal as your null. Select a level of significance that was given to us, 0.05. Step 3, sketch your rejection region. This is lower tailed, so rejection region on the left. And our sample statistic has a z distribution. So again, this is the p-hat distribution here. Those are p-hat values, and that's got a normal distribution. So we can go back to our test of common rejection regions. So there's our common rejection region table, brought that down from above, and 0.05, lower tailed test right here, negative 1.645. So our critical value here is negative 1.645. We'll go ahead and compute our test statistic now. So p-hat we need here, so let's see, p-hat is going to be 22 divided by 500. And compute that real quick. So 0.044 is our p-hat. So on the top, 0.044, minus 0.056. And then in the denominator, we've got our standard deviation. So that's going to be 0.056, 1 minus 0.056. And then we are dividing by 500 our sample size. So compute that on the calculator. So let's do alpha y equal enter to get our horizontal fraction. So 0.044 minus 0.056. In the denominator, we have a square root, 0.056, parentheses, 1 minus 0.056. Close it up, divide by 500. So negative 1.167. And that'd be about right here. So there's our z-test. And we notice that is not in the rejection region. It's not extreme enough. So step 5, we say that our z-test here, which is negative 1.167, is greater than the negative 1.645. So we do not reject. H0. So interpret our conclusion then. We do not reject, so there is not sufficient evidence to conclude the alternative hypothesis that P is less than 0.056. So in other words, the new screen is not better.